Daiwadag post-tensioning systems are engineered for high-performance bridge structures, delivering high pre-stressing forces and accommodating long tendon lengths. During installation, jacks and pumps operate near maximum capacity, requiring continuous service and inspection to maintain precision and reliability. Grouting operations are critical for durability, ensuring that post-tensioned elements achieve long-term structural integrity. Daiwadag's expertise extends to stay cable systems for cable-stayed bridges, where DynoBond and DynoGrip cables provide replaceable, efficient tensioning for lightweight superstructures. On major projects such as the 2.6-kilometer Sky Bridge crossing, Daiwadag supplied formed travelers, post-tensioning systems, and supervised installation, supporting advanced methods like free cantilever construction. Every aspect is designed to combine technical efficiency, safety, and economic installation, meeting stringent quality standards. Construction of the St. Croix Crossing Bridge involved extensive underwater foundation work, connecting St. Joseph, Wisconsin, and Oak Park Heights, Minnesota. The bridge piers rest on caissons extending up to 140 feet below the water, with 4 caissons per pier and 10 pier columns in total. Crews floated in a prefabricated steel framing system topped with concrete, which served as a work platform with circular openings for placing the steel casings. These casings penetrated up to 25 feet of water, 87 feet of muck, sand, gravel, and soft sandstone before reaching bedrock. Excavation inside the casings removed 500 dump truckloads of material, and massive drill bits, up to 7.5 feet in diameter, were used to drill 25 additional feet into bedrock. Reinforcement cages were installed and concrete pumped to form solid foundations. Cofferdams were placed around the prefabricated deck, and a 3 to 4 foot thick concrete seal was poured underwater. Once dried, reinforced footings and pier columns were constructed, supporting 400,000 tons of bridge weight and ensuring structural durability for over 100 years. The world's first Kiloton bridge girder erection machine has been commissioned in Fujian Province, southeast China. Designed for the Meizu Bay Cross-Sea Bridge on the Fuzhou-Xiamen high-speed railway, the machine measures 40 meters in length and weighs over 1,000 tons. Engineered for precision and efficiency, it lifts and positions massive bridge girders, accelerating construction timelines and ensuring structural safety. The high-speed railway is scheduled to commence operations in 2022, marking a significant milestone in advanced bridge construction. Spanning the busy Saigon River in Ho Chi Minh City is a landmark cable stay structure and a crucial component of the city's ring road, linking the Mekong Delta to central and northern Vietnam. Built between 2007 and 2009, it was the first major privately funded bridge project in the country. Designed and constructed by the BBPH Consortium, comprising Germany's Bilfinger Berger and Australia's Balderstone Hornibrook, the project leveraged extensive international experience, completing months ahead of schedule and within budget. The bridge's roadway is suspended from high-strength cables attached directly to towers, which bear the entire load. BBPH's prior experience with cable-stayed bridges, including Sydney's Anzac Bridge and the Centennial Bridge in Panama, allowed optimization of processes and faster learning curves. After completing deck work and cable installation on District 7, massive travelers had to be transported and repositioned to District 2, a delicate operation requiring precision, heavy lifting equipment, and careful logistics. Each transfer took roughly a week, and any equipment damage would have significantly delayed the project.
Oh, oh, got it. Oh my God. Here. Thank you.
When in doubt, look in your own canoe.
Uh-huh.
Thank you. Hard. I tried so hard to get here. And we were beaten by Rob. At least we were
Paddle away.
By May 19, 2009, deck closure was completed, marking the bridge's readiness for traffic. Stretching 2.1 kilometers, the Hugh Mai Bridge now connects District 7 and District 2, dramatically improving traffic flow while standing as a modern engineering landmark. Its construction highlights advanced post-tensioning techniques, meticulous coordination of heavy equipment, and optimized cable stay installation, demonstrating Vietnam's growing expertise in large-scale infrastructure. Beyond transportation, the bridge symbolizes Vietnam's progress and commitment to world-class engineering standards. The Beachwood Boulevard Bridge in Greenfield was a complex infrastructure project requiring precise engineering and careful sequencing to ensure safety and efficiency. The bridge spans a local waterway and accommodates both vehicular traffic and pedestrian pathways, making it an essential component of the area's transportation network. Construction began with detailed site preparation, including excavation for abutments and piers, and installation of cofferdams to manage water flow during foundation work. Foundations were established using reinforced concrete caissons driven into stable soil layers, providing a secure base for the bridge. Steel rebar cages were carefully positioned inside the caissons before concrete was poured, ensuring maximum structural integrity. Once cured, these foundations supported the erection of precast concrete segments and steel girders. During the superstructure construction phase, the steel beams and floor girders are pre-assembled on the ground, then lifted and placed into position in the weekend highway closure scenario. The erection of the arches and girders is done precisely using lifting equipment, creating a solid and continuous structure. The bridge's superstructure utilized a combination of steel girders and pre-stressed concrete beams. Heavy lifting equipment positioned each girder with millimeter accuracy, while temporary supports maintained alignment during installation. Post-tensioning cables were then threaded through ducts within the beams and tensioned to provide additional strength and minimize deflection under load. Deck construction involved placing formwork and pouring high-strength concrete, followed by finishing and curing. Expansion joints, drainage systems, and safety barriers were installed to meet design standards and ensure durability. Throughout construction, strict quality control measures were applied, including material testing, alignment verification, and load testing. By integrating modern construction techniques with careful project management, the Beachwood Boulevard Bridge was completed efficiently, providing a safe and durable crossing that enhances connectivity in Greenfield, while demonstrating the precision and technical expertise required for modern bridge construction. Duff's Bridge and Marley Bridge over Dingo Creek were handed over to the Greater Atari City Council in 1989. Both were single-lane Allen timber truss bridges, increasingly expensive and difficult to maintain due to the high-quality timber and skilled labor required. Marley and Duff's bridges, completed in 1900 and 1926 respectively, were the council's last remaining timber truss structures. Restrictions imposed on heavy vehicles, reducing load limits from 25 tons to as low as 2 to 12 tons by 2008, highlighted the urgent need for replacement. These restrictions impacted local businesses, farms, rural communities, and tourists. With 2 years of future bridge funding and a $2.5 million grant, the council proposed replacing the bridges to provide safe, reliable, and cost-effective infrastructure. The project began with extensive site investigations and options analysis, focusing on three key criteria: cost, functionality, and traffic impact. Three-span, two-lane bridges were selected for both sites. Marley Bridge was retained on its existing alignment to save approximately $1.4 million in approach roadworks, while Duff's was initially proposed on a new alignment downstream to facilitate construction access for heavy plant, precast items, cranes, and concrete trucks. During design, an indigenous artifact was discovered along Duff's downstream alignment, prompting the project team to shift the new alignment onto the existing route. This minimized environmental impact and avoided delays, while enabling the bridges to be designed nearly identically, optimizing construction efficiency. Foundations for both bridges relied on permanently cased large-diameter board piles penetrating 3 meters into bedrock, recommended by regional GE Technical Solutions. This method also mitigated scouring risks from Dingo Creek's fast-flowing waters. 2 piles per pier were installed on either side of the existing timber decks, eliminating the need to drill through the old structures and improving safety by reducing time spent near traffic. Steel-encased concrete piles were extended to the headstock level. The use of precast members minimized in-water work, reducing exposure to flooding and high-risk height operations. Site preparation included installing crane pads, temporary support structures, and storage for precast components. Demolition of the old timber trusses was complex due to unpredictable truss behavior, as elements transitioned from tension to compression during lifts. Each span required detailed analysis, engineering sign-off, and careful propping, strapping, and chaining. Duff's bridge, over 16 meters high, required a licensed company and a 500-ton all-terrain crane for span removal. Spans were lifted, lowered, and disassembled at ground level to improve safety, while temporary steel supports were erected to stabilize the trusses during demolition. Where the crane lacked sufficient capacity, spans were cut and removed in 2 sections. At Marley, demolition improvements included reduced crane standby times and innovative temporary support structures. Steel headstocks were integrated into the permanent pier design to support temporary steelworks, allowing reuse of the same structures for both bridges. This minimized risk, cost, and construction time. The process incorporated lessons learned from Duff's, including time-lapse analysis to identify critical path activities. Marley's timber truss was dismantled with a restricted license using a 60-ton crane, with careful removal at ground level, reducing height work and enabling reclamation of sound timber for sustainable reuse. Construction of the new decks relied on precast, pre-stressed concrete planks with transverse post-tensioning bars, eliminating the need for in-situ decks and allowing immediate traffic access after installation. Edge planks were lifted using scaffolding for safe access at height. Pre-routed transverse bars encased in PVC sheaths provided long-term corrosion protection, while grouting under a 100 kilonewtons load ensured plank consolidation. Bars could be replaced in the future if maintenance was required. Conduits were installed in transverse bar holes to maintain alignment. and small hydraulic jacks against fabricated steel blocks ensured precise placement. At Marley, a second 200-ton crane lifted distant spans working near maximum capacity due to the congested site. Trial assembly of precast planks in Brisbane allowed fault correction and ensured quality control before on-site installation. Scaffold crews immediately installed infills for safe working conditions, while precast abutments, headstocks, and curtain walls reduced closure time. Precast production efficiency was maximized by casting identical planks, minimizing variations in length, skew, or penetration, reducing cost and delays. The heavy lifts at Marley were completed with the 500-ton crane used at maximum efficiency. Barrier rail sections were pre-assembled and installed before scaffolding removal, and all infield formwork was cast with corrosion protection caps for future maintenance access. Duff's bridge reopened after 7 days of closure, while Marley used the full 10-day window to install headstocks, decks, and guardrails. The strategic use of temporary steel support structures allowed them to serve as emergency crossings, providing sustainable infrastructure reuse and community resilience. Flooding events in early 2013 did not affect completion dates or costs due to careful planning and minimization of in-water work. Deck widths were increased to 2 lanes, and design loadings accommodated 44-ton trucks and 68-ton B-doubles, enhancing safety and supporting local economic growth. Flexible joints, guardrails, and signage completed Marley Bridge, achieving high-quality, innovative solutions normally seen in larger infrastructure projects. Continuous improvement throughout the project ensured long-lasting, cost-effective community infrastructure. The UAE's first overseas railway bridge is under construction, linking Khalifa Port to the national railway network. Part of Package B of the Etihad Rail project, connecting Tarif and Said Shuaib, this 1-kilometer-long bridge will enhance freight transport efficiency, speed, and reduce trade costs in the region. Currently, 50% of the bridge's construction is complete. The project will use approximately 18 300 cubic meters of reinforced concrete and 4 117 tons of steel, making it a major engineering milestone for UAE's infrastructure and regional logistics development. The Shah Ruace railway line, a key segment of the UAE's Etihad Rail network, involves highly coordinated engineering and construction processes to ensure a durable, safe, and efficient rail corridor. Construction begins at the welding plant, where prime rails are carefully loaded, handled, and prepared for joining. Flash butt welding is employed to form long, continuous rails, ensuring high-quality, consistent rail connections critical for high-speed and heavy freight operations. Once welded, the rails undergo grinding to achieve smooth joints, maintaining track alignment and passenger comfort. On-site rail unloading and sleeper placement follow. Sleepers are positioned precisely, maintaining proper gauge and spacing before rails are laid on top. Fastenings are initially fixed to secure the rails, allowing further operations such as aluminothermic welding for final joining. After welding, fastenings are released temporarily to allow stress relief and rail alignment adjustments. Subsequent ballast layers are distributed along the track bed, with the first layer providing foundational support and drainage, followed by tamping to compact and stabilize the track. A second ballast layer is then applied, leveled, and tamped to ensure uniform load distribution. Track leveling, alignment, and dynamic stabilization are performed, guaranteeing smooth operation under heavy freight loads. Ballast profiling and track brushing remove excess material, while vacuum cleaning ensures sand and debris do not interfere with rail performance. Topographic surveys are carried out throughout the construction process to monitor track geometry and ensure alignment with design specifications. Rails are cut and installed where required, with rail pullers used to adjust rail tension. The track is then de-stressed to release residual stresses from welding, minimizing the risk of track deformation over time. All welding operations, including aluminothermic welding, are subjected to rigorous quality control, ensuring weld integrity, dimensional accuracy, and alignment. Construction railway operations are carefully managed, with a dedicated traffic office coordinating train movements and shunting operations at turnouts. Safety remains a top priority, with a zero-accident philosophy embedded across all work phases. Personnel undergo safety induction and adhere to strict operational protocols during all stages, from welding and ballast handling to track leveling and final inspections. Once the primary track installation is complete, final quality checks ensure all rails, fastenings, and sleepers meet strict tolerance requirements. Track dynamic stabilization is performed to simulate train operations, ensuring the track responds correctly to load and vibration. Additional ballast adjustments, sanding, and vacuum cleaning are undertaken to remove debris and maintain track integrity. The final stage includes comprehensive safety and operational testing. Fastenings are checked and retightened where necessary, and final controls confirm alignment, gauge, and weld quality. The construction of the Shah Ruace line is a prime example of modern railway engineering, combining mechanized processes, precision surveying, and rigorous quality control. Each stage, from flash butt welding at the plant to ballast profiling on site, contributes to a reliable, high-capacity railway capable of supporting both freight and passenger services in the UAE. Throughout the project, advanced construction methodologies, including automated welding, mechanized track laying, and dynamic stabilization, ensure efficiency and minimize risks. The use of high-quality materials, careful planning, and adherence to international safety standards has enabled the Etihad Rail project team to deliver a robust infrastructure asset, connecting industrial hubs, ports, and logistics centers, and supporting the UAE's economic growth and regional trade objectives. By integrating safety, precision, and technological innovation at every stage, the Shah Ruace railway line demonstrates the UAE's commitment to world-class infrastructure development, providing a modern, reliable rail link that will serve the country for decades to come.